This is ELEC 1510 Logic Design Lecture 8 Video 2 on NOR implementations of circuits, corresponding to textbook section 3.6. NOR gates can be used almost exactly like NAND gates, except they are basically just forming the opposite of all the rules. So anything that had an AND as the operation for NAND gates, now if we have an OR, we can formulate it as a NOR gate circuit. So that means that sum of product circuits lead to a NAND gate implementation, and product of sum circuits lead to a NOR gate implementation. So for example, NOR gates are OR gates with complemented outputs. So if we want to implement X or Y parentheses prime, we would input X and Y to an OR gate and complement the output, making it a NOR gate. We can have more than two inputs on a NOR gate as well. So W, X, Y, Z, all input to an OR gate with a complemented input, and that is a 4-input NOR gate. Just like with NAND gates, if we want to complement a single term to create a complemented literal, we can just input that single variable into both inputs of a NOR gate, and that will create its complement. So that means that when we design circuits that have complemented literals, those complements can be created using NOR gates. So that doesn't mean that the circuit implementation has gates in it other than the NOR gate. So let's look at how this works using DeMorgans Theorem. If we take the term x, y, z, that would normally be implemented using an AND gate. So x, y, and z are all input to an AND gate. Now, if I double complement all of those inputs, the double complements cancel out, so I'm not modifying the expression at all, but visually this can be represented as complementing all of the inputs. So again, you could do that using NOR gates, and then adding bubbles to the input of the AND gate. But then when we take the DeMorgans theorem on this term, we would get rid of one of the complements for each variable. We would change the operation to OR, and we would complement the output. And so when we draw this function, we get x prime, y prime, and z prime as inputs to a NOR gate. So what that means is that an AND gate with complemented inputs is the same thing as a NOR gate, just like an OR gate with complemented inputs was the same thing as a NAND gate. So it's just the dual of the same thing that we did with NAND gates. So let's look at an example of how to use this to create a NOR gate circuit out of a product of sums expression. So our product of sums expression is parentheses x or z prime and parentheses y prime or z and x prime. Now if you multiplied this out, you could probably simplify it somewhat, but right now I'm not interested in simplifying this function, just implementing it using a logic circuit. So let's apply a double complement to this expression, x or z prime and y prime or z and x prime, all double complemented. Now when I apply DeMorgans theorem, I distribute one of those complements inside the brackets and change the operation. So I will get x or z prime prime or y prime or z prime or x double prime prime, and the double prime on the x will cancel out. So now when I draw this as a circuit, you can see that every single operation is a NOR operation. So I have x or z prime prime, that's a NOR gate. Then y prime or z prime, that's also a NOR gate, and then just x. And all of these are going to be inputs to a 3-input NOR gate. And so I have implemented this product of sums expression using all NOR gates. If I want to do that same thing visually, I can draw out this circuit in its normal product of sums form. So that means that x and z prime are inputs to an OR gate. Y prime and z are inputs to an OR gate. And x prime is on its own. All of those are inputs to an AND gate. And now I know that an AND gate with complemented inputs is equal to a NOR gate. So I need to complement those inputs by adding bubbles to the inputs. And now, in order to make sure that those bubbles are canceled out and don't affect the equation, I need to add bubbles to the other end of each of those wires. So I'll add a bubble here, add a bubble here, and add a bubble here. Now, as you can see, these are NOR gates, and an AND gate with complemented inputs is equal to a NOR gate. So when I redraw this circuit, it's going to look like this: x, z prime, y prime, z, and x, because the prime here and the bubble cancel each other out. And I ultimately end up with the same circuit that I had derived on the previous slide. So you can perform the transition from a product of sums implementation either algebraically or visually by adding bubbles, just like we were able to transition from sum of products into NAND circuitry either algebraically or visually.